Good morning. It's Sunday morning, day 17 of Advent of Code. My name is Thomas and my guests today are Frank and Achim. Good morning.
Good morning.
Good morning.
So, Frank, can you explain us and the world the riddle for today?
Yeah, the riddle for today is again something with the grid and pathfinding. So it's called Clumsy Crucible, and we are presented with a map like this, a map of digits. Each digit is one cell in the map or in the grid. And now what we have, we start in the left upper corner and we have to reach the lower right corner. And if we step on such a field, then the number in this field counts toward the sum of field values. So what we try to find is the cheapest path, the path where the numbers sum up to the smallest number. So that's a kind of simple problem so far, but now there are some extra rules. The extra rules are that we can step at most 3 positions in one direction. So if we are here, then we can step on the 4, on the 1, or on the 3. And then we have to change direction to the right or left or any other direction, but not the opposite direction. So to the left or to the right.
There is a need to change the direction.
Yeah, so we can go from the 2 to the 4 to the 1 to the 3, and at latest at the 3 we have to do a turn right and then go down. And then we can again go 1, 2, or 3, and then we can turn left or we can turn right. So we can reach every position. We can go in circles, whatever. We can go where we want, but not more than 3 steps and not in the opposite direction. We cannot go down and then directly up again. So we have to consider this while we calculate where we can go to, and then it's basically the Dijkstra algorithm. So we try to find the cheapest path from start to end, and after we checked all possible paths and so on, then the best value in target position is the answer. So and then I will explain the second part also, because it's not much different. In the second part, basically everything stays the same, but now the rules are a bit different. We must go at least 4 positions in one direction and must not go more than 10 positions in one direction. So it's basically the same problem with some other numbers, which makes it from the implementation wise a bit bigger. This is the twist in the second star.
Okay.
So now I will. Yeah.
Before you show the code, is there some comment from Achim?
Not so far.
Okay.
Okay, now I represent the code. This code looks pretty generic, like an Dijkstra algorithm looks. So what we do, we maintain a map of states, and for each state we store what was the cheapest path to reach this. So for example, I mark this 5 here, which may be at position 6, 5 or something. Now the state to reach this position is first of all, the position is in the state. Second, the direction from where we come and with how many steps we come is in this state within. So I implemented this as a multi-dimensional array here. I call this DP for dynamic programming. And I organized it in a way that I said on the lowest index, I store the number of steps in the north direction, and then in the east direction, and the west direction, and the south direction. And final 2 dimensions is the I position, so the direction east, number of steps, and direction south, so the position of this field. And then for each such state, I got a minimum value with which I reached it. And now if I am at a position, say this thing here, then I try to go in all directions several steps, and I can check from the state where I came from and where I go to if this is possible. So if it's more than 4 steps or less than 10 steps, and then I reach some other field and can tell, okay, I was there with a better value or not. And if I was not there with a better value, I take my new value and put it back on my queue with all the states. And this basically then is the Dijkstra algorithm. Here looks like this because the bit complicated, because this construction of which steps are possible, which are not possible, is a bit clumsy. You see here, I take the current step and then I check all number of steps from 1 to 10 to go that direction, that length, and then in all 4 directions. And then I have an extra rule to not go in the opposite direction. So if I not go in the opposite direction and the number of steps I previously took plus the number of current steps is bigger than 4 and smaller or equal than 10, then I know I got an like a legal move, or in terms of the algorithm, it's 2 nodes in the graph which have an edge between them. So then I can calculate my new state. So the new state is the new position, and these movement values. So which direction, how many steps. And if the value from this target state is bigger than my current state, then I know I found the new shortest path for this position and this direction. And I enter the state and put it on the queue, and then I loop again. And in the end, I have to find for the right down corner, this is the last 2 dimensions of my array, and for all other dimensions, the minimum value, and this is then the answer. This works for both stars. So for the first star, we have to enter here in the loop some smaller values. Then it's not 1 to 10, it's 1 to 3, and I have to change this condition, but else it is the same.
Can you repeat the name of the algorithm you used?
Dijkstra is it called.
Dijkstra.
It's basically a BFS traversal of the tree, but what we do here, this queue with the states is not simply a queue where you take always the first state and push the other states on the end, but instead it's a sorted list. And this list is sorted by the value. So what I do here is always take the cheapest path that I already found in sum. That is the one I take as the next step to check to find further things. And this is usable in this algorithm because it makes it much faster. If you use a simple queue here, then you calculate a lot of states, and then you calculate in the beginning another state, and then these all states you calculated before point out as useless, because in the first level of the tree you had a better choice. And if you sort it here, I did it with a B tree set, it's called in Rust. In Java we would use a tree set probably, or simply a priority queue. Then this becomes a bit quicker, and this is part of the Dijkstra algorithm. Yeah.
Okay, thank you. Achim, comments from your side? Questions?
I didn't really use the Dijkstra algorithm because I really have to look it up how it works. My implementation has a bit less code, but runs slow as hell. For a single solution on the real data, I need something between 2 and 3 minutes.
Okay. Some last words from you, Frank?
I felt a bit like yesterday's problem, because yesterday we had also some pathfinding in the grid, and then we had to include the direction of the movement into the state. And now today it was not only the direction, but also the number of steps in the direction. But else it was basically the same problem, or at least very similar.
Okay. Then thank you to you both, and we see us tomorrow.
Bye.
Bye.